So temporal summation and spatial summation are just the two main ways neurons add up incoming signals. So temporal summation happens when the same presynaptic neuron sends the signal several times very quickly. Because the signal is so close together, the first EPSP doesn't have time to fade before the next one arrives. So they stack on top of each other. So it's like a constant, like, well, they're like stacked on top of each other. While spatial summation happens when different presynaptic, like neurons, send signals at the same time. That just scared me. To different spots on the dendrite. In this case, each EPSP is small and on its own, but when they happen together, they add up and can push the neuron closer to firing an action potential. And the reason, like, the time constant is important is because it tells us how long a change in voltage lasts in a neuron. So a larger time constant means the voltage change fades more slowly, and that gives multiple signals more time to overlap, and together they make a summation more effective. So when there's like a shorter time constant, it won't give enough time for neither temporal or spatial summation to occur. And when we have a longer time constant, that space there will allow spatial or temporal summation to occur within that time frame. And then dendritic filtering is how dendrites change synaptic signals as they move towards the cell body. Signals that start far away from dendrites usually arrive to the soma weaker and slower, which is like our distal dendritic filtering. Um, and because of this, the synapses close to the soma have a strong effect on whether a neuron fires an action potential. So proximal, um, our proximal dendritic filtering. So the slower signals, like which are farther away from the synapse, can add together more easily over time. So they often show a more temporal summation than fast close by ones. So our distal ones would show a closer look to temporal summation. This means that like the location of the synapse changes how much it can influence the neuron. So if we have a proximal, like a proximal filtering or dendritic filtering, then we'll see a faster occurrence of like the signals, and then we would see with distal, because it takes like a much longer time for, if we have the cell bodies here and we have like our proximal here and then we have our distal here, well, the average, like, it's just going to take longer for like the message to move, or like for the signal to be sent from our distal than from our proximal. Um, so there's also some neurons like the pyramidal cells, CA1, CA1 pyramidal cells. And they adjust for this by making like far away synapses stronger, so that their signals aren't reduced by filtering. So these neurons are like creating their distal signals much stronger, so they could kind of compensate for the fact that they're farther away than the proximal ones, which would have like maybe a lower, like, which have like a lower like signaling rate, or like just a lower like signal. And that's just because they're just like compensating from the fact that this distal this distal um section would like just create a stronger would push in like the stronger force, the stronger signal, so it could compensate for the fact that it's so far away. Also, the structure of dendrites changes with distance. We see that close dendrites have mixed like microtubule directions, while far dendrites have microtubules all pointing the same way. So that also comes into play with taking into consideration dendritic filtering. Um, so like if we have like far away like dendrites, then we'll have like right the microtubules pulling all the same way, but then we have closer dendrites, we have mixed microtubules going every direction. So it might be like harder for like it might be a little more difficult for signals to like kind of reach the soma. Or I guess they had to go around maybe more pathways rather than like a distal one is direct into the um into the soma.